So good morning and welcome to Mass 802, Algebraic Topology. So yesterday we talked about operations on spaces. We look at quotient spaces, and then we also look at adjoint spaces, adjunction spaces, and then that is we also look at connected sum, something we call performing surgery on manifolds. So actually, that section of the discussion was just to tell you about different type of topological spaces, and the most important one are the topological manifolds, which we have defined. So we have seen the closed balls and the spheres, the open balls. We have also looked at cylinder, which can be also called a strip, and then we have looked at Mobius band, and then we saw Klein bottle and real projective plane, and then we have also looked at cell complexes, other ways of constructing topological spaces. So today we are going to start looking at homotopy and homotopy equivalence. So this is the second part of our discussion, homotopy. Thank you. So the first section, so what we are going to be doing is to look at some weaker notion of homeomorphism. You remember in our introductory class, we talked about the main fundamental problem in topology is to identify spaces, which spaces are homeomorphic. So while we want to know whether two spaces are homeomorphic, it is much better in the theory to generalize the notion of homeomorphism to the notion of homotopy. So homotopy is a very weaker notion of homeomorphism. Whenever spaces are homeomorphic, they are homotopic, but you will have many spaces that are homotopic but not homeomorphic. We will define the notion and then we'll see what it is. So, so we will look at homotopy, and then we start with the definition of what a homotopy is. So a homotopy is a continuous map. You remember our convention, even if I just say it's a mapping, we understand continuous mapping. It's a continuous family of mapping, not just one single mapping, but family of maps. So family of continuous mappings. FT from X to Y. Well, since we are talking about continuous mappings, already it is understood that X and Y are topological spaces with their corresponding topology. And this family is indexed by the interval I, which is this. So once you have a continuous family of continuous mapping from one topological space to another topological space, that is called homotopy. Okay? All right. So I think the only thing we need to make precise is what we mean by continuous family. We know what continuous mappings is. So each one of these FT is a continuous mapping from this space to the other. But then by continuous family, we mean the associated map. So you should understand that by continuous family, we mean the associated map. So F from X cross I into Y given by, because given such a family, you can always define this mapping since T is coming from the index set 0 to 1. So you can define the mapping F of X comma T to be equal to Ft of X. So we mean this map is continuous. Continuous in the sense that X cross I is a topological space given the product topology. So you know this one is a subset of the set of real numbers. So it has the subspace topology or relative topology. Now this one already is a space with its own topology. So you can think of the product topology. So with respect to the product topology, and you already have a topological space as the output. So we have a continuous map. So by continuous family, we mean this mapping is continuous. I hope it's okay. It's okay, Paul? So it all, you can think of it that, well, it is continuous is in both variables, in the first and the second variable, continuity. So this is what we mean by continuous family of mapping. So any such family of maps from X to Y is called a homotopy. All right. If you have the homotopy, then the maps F0 and F1. So, well, in the family, you know, the first guy in the family is F0, and the second guy in the family is what? F1. These two mappings are called homotopic. Homotopic. Written as, we write that as F0 is homotopic to F1. Okay, please take note. The maps are called homotopic, not the spaces. I hope it's okay. So if you have a homotopy, then the first mapping in the family and the last mapping in the family are called what? Homotopic, not what? The spaces. So the mappings are homotopic. If in a homotopy there is a subset A of the space X such that the homotopy, that is, each one of this mapping is independent of you know, is not doing anything. The mappings, all of them are doing the same thing on the subset A. Then the homotopy is said to be relative to A. That is F T restricted to A is independent of T. Then we say that F0 and F1 are homotopic. But relative to the subset A. All right, please. What we are saying is, if you have a subset, you see this is a map from X into Y. So if you have a portion of X that, the image throughout the mapping, the homotopy, that portion of X is what is happening with that portion A of X is the same. So what F0 is doing to A is distinct as what Ft, for all T. So the mapping restricted to A is the same throughout. I hope it's okay. It's not depending on T. That is, whichever Ft you pick, whatever the output on A will be, it is always the same. I hope you are following. So then you now say the homotopy is relative to that subset A. Okay, let me give you an example to demonstrate the concept. So let us see an example of this. So you can imagine your set A, the X can be the set. So you can take X to be this topological space, the subset of the two-dimensional Euclidean space, like a thick A. So I mean this portion of the Euclidean space. And then Y can be just an analysis. Then you can define a family of maps, Ft, from X into Y. That family of mapping exists as if you are deforming this to that. I hope it's okay. You can continuously deform this to that shape. Maybe in the first, so that mapping, that family is what we call a homotopy. But if you look at this cycle as your subset A, throughout the mapping from A to Y, this cycle here, is always mapped to that. So F0 is still sending the cycle here to this cycle. And F1 is also doing the same, and all the other Ft are doing the same. So you will always have a homotopy relative to A, this cycle over there. I hope it's okay. So this is what we call a homotopy. Any family of mapping that is continuous and doing this. Okay? Or you can think of it as Y is already a subset of A of X. Okay, let me define the concept of retraction before we. So a retraction of X of a topological space. So X is a topological space onto a subset of the topological space, subset A of X is a map. And then by a mapping, we mean a continuous map, R from X to X, such that R of X is equal to A. And R restricted to A is the identity on A. This is how I write identity on A. Okay? So, any such mapping is called a retraction. So, that is R square is equal to R. It's just like a projection. The concept of retraction is just like you are having a projection because it is identity on A and the entire space is mapped to A. So that means R square will always be equal to R. So it's because it's identity on its image. Yeah, it's a self mapping, but mapping into a subset and then fixing the subset. It's not changing any point on the subset. Yeah. So think of like this disk. If this X is the not disk, the annulus. So you can see on the annulus, you have this inner cycle here. This cycle. You can take that to be your A. So you can define a mapping R from X to X such that every point along this line will map to this point here. And all points along this line will also map to this point here. So at the end of the day, the entire space will map to this inner cycle. And points on the cycle are left unchanged. I hope it's okay. So that mapping, that will just drop everything down to the cycle at once without changing the point on the cycle is what we call a retraction. Retraction of the entire space onto what? Onto the subspace A. I hope it's okay. So that is what is called retraction. You can also think of like the A over there. In the book, this is also there. This example, you can think of having a thick A and then there is a thin A sitting inside as a subset. So where this thin A is our subset A and the thick A is the space X. I hope it's okay. So you have the subset A here and this is your space X. But then you can define a mapping and send all these points down to this point here and all the point here. So you can think of mapping all these points down to A and all these points down to the thin A. But then at the end of the day, once you do the mapping R, everything is mapped the thin A. Okay? Everything on the thick A is mapped to the thin A. So we say we have a retraction. And when you are mapping, the mapping R is not changing the point on A. So it's acting as identity on A. So it's like everything is being projected down to A. The entire big space is projected down to the subspace while keeping the subspace fixed as it is. I hope it's okay. So that is what a retraction is. Okay? So this is the concept of retraction. Now, so once the concept of retraction is understood, then we now move to the next concept, which is called deformation retraction. So a deformation retraction is a homotopy. Meanwhile, we have already defined what a homotopy is, so that is understood from the identity, so well, if you want to say a deformation retraction, it should be of a space. So a deformation retraction of a space onto a subspace. A deformation retraction of a space X onto a subset A of the space, just like, like before, like when I defined the retraction. It's nothing but a homotopy from the identity so a homotopy from the identity to, from the identity where, which identity? This identity on X, on the entire space. So the initial map in the homotopy F0 should be the identity. Is that okay? To a retraction, to a retraction. Retraction of a retraction R of the source of the space X onto A. So that is a deformation retraction is a homotopy. It's actually a homotopy FT from X to, well, it will be X. Since you have one space here. So it's a homotopy from X into X, or onto X, such that, but then, you know, this is indexed by T, intervals 0 to 1. So it's like you are thinking of this process is happening in a time interval, like an hour interval, okay? In 1 hour time, you are able to deform the entire space such that, so if you have a continuous family like this, so that is a continuous family, because that is what we call homotopy. So a continuous family of continuous maps, such that the first mapping is the identity on X. So it is a homotopy from the identity, and the second mapping should be a retraction. The second map, F1, should be the last map, I mean, because this is a homotopy from F0 to F1. So the last mapping should be a retraction, meaning what? It should map the entire space to X, and that it should fix A. It should what? Fix A. So F1 should be a retraction. So it should fix A. Ft of restricted to A is the identity on A for all T. For all T. Well, but this that we have mentioned here is saying that all the continuous mappings in the family are fixing A, not only the last one. Because, but actually the definition is only required that the last one, because it's a homotopy from the identity to a retraction. So it should have been F1 of A, F1 restricted to A should be equal to the identity on A. Are you following? But then, if you impose this condition that even each member of the family should fix A, this is usually called strong deformation retraction. So strong deformation retraction. So that is it. But you know, already when you say this, it means F1 restricted to A is also equal to the identity on A. So this is what we call a deformation retraction. So a deformation retraction is this kind. Okay? Is it okay? All right. In fact, look at what is going on here. So you can think of a whole family of maps. Let me demonstrate it here with this. So F0, everything is on not change. Are you following? But it's mapping everything now at time t equal to half. This is shrinked down to. So it may be like shrinking this annulus. You are continuously, you started with the identity and you are continuously shrinking the annulus. So this is what F1 will do. Let me just, to the cycle, you are shrinking it to the cycle. So like F1, so this is the annulus, and then F1, F0 is not changing anything, the same annulus. Okay? But F1 will reduce it in size. So, but let me jump F1 and do F half. Halfway in the process, it is now almost shrinking down to, because everything is coming down to the central cycle. So F1, it did not change anything. But then F half has almost gotten the entire space to the cycle. But notice that members of this central cycle are fixed throughout the process. F what? 3/2 is going to be, so almost there. Or you can think of it like as if you are almost at the cycle. So that is how it will continuously, since this is a continuous time interval, and then F1, you are already at the cycle, which is your A. But throughout the homotopy, nothing is changed. You know, nothing happened to A. I hope it's okay. Nothing happened to A. So that is what is going on. So it's like you are deforming everything. But you know, deformation retraction, it's only saying that you should deform from the identity to a retraction. Because once you arrive at a retraction, it will collapse everything to A. Like if you are doing it, if this one is happening. So if like you have a mapping, like we thought of having a retraction here. So let me demonstrate it over here. So you remember we said there is a retraction from this space, from this space down to where? To this one, which thought of as a subset of this. So we have a retraction like this. But then I can think of some space like this. And then I can have a homotopy that will take this to that space. I hope it's okay. That will take this to this map. So that will start from, I can think of a homotopy because you can do the deformation. I don't know whether it's the same thing. Okay, let me just do it one more time. You have, so I want to draw the same thing, a copy of that one. Think of it as a copy of what I have drawn here, so that I have my F0, which is the identity on X. This is my space S and this is my space X. Okay, this is some other space. But I know that I have that A inside here, that my thin A as a subset over here. So my thin A is already existing as a subset over here. You know, thin A is already existing as a subset here. But then you now have the identity from X to X. And you can, the next one, you know, F half. By F half, you are almost deforming this thing to this shape. I hope it's okay. So you can start doing the deformation until you arrive at this shape. But once you arrive at this shape, you know that you are having a retraction down to A. Are you following? So if you have a homotopy from the identity to a retraction on A, that is called a deformation retraction. I hope it's okay. So you don't have to continue to be doing deformation until you arrive at the cycle. This is what I'm trying to say. But you know, you can do the deformation continuously, because once you arrive at the retraction will not have to eventually get the space to the thing A. The retraction will just send all the point at once down to A. But then it can still happen. Once you arrive at a retraction, everything will collapse to A automatically. I hope it's okay. So that is what we are saying. So which means we can deform this space onto the thin A. I hope it's okay. So this is the idea of deformation retraction. So how many concepts so far? We define homotopy as just a continuous family of maps indexed by time t from 0 to 1. You know? Okay? So once you have that continuous family of mapping, is what? It is called a homotopy. And the first map, F0 and F1, are called homotopic. So you can just look at two mappings, F and G, and then regard this as F0 and this as F1. So if you can have a homotopy that will start from F and end at G, then F and G are called homotopic. I hope it's okay. And then, if in the process of the homotopy, there is a subset of X, the F0 is mapped to, you know, the image. So the image of this set, subset A of X, is not changing with time. That is fixed. It remains fixed. You remember how we wrote it? We say Ft restricted to A is independent of T. So which means if there is a set that once mapped by F0, it remains to be the image of that set throughout the homotopy, then we say the mappings are homotopic relative to that subset. I hope it's okay. So that is the second concept we said, and then we define retraction. So a retraction is that mapping that will collapse the entire space to a given subspace. But the mapping should be continuous. So I always have to warn you that anytime I say a map in this course, I'm talking about continuous mapping, because this is topology. I hope it's okay. So that mapping that will collapse the entire space to a subset in a continuous fashion, that mapping is called like this map here, that will collapse everything at once to the inner cycle. Or you can do it by expanding everything. It can also collapse everything to the out cycle. It's still the same thing. You can reverse the process and collapse everything like this to the big cycle. Or in a continuous fashion, you can do that. So so this space can be retracted to the cycle. I hope it's okay. So that is called a retraction. And then if you have a homotopy that starts from the identity map and end at a retraction of the entire space onto a subspace, then that homotopy is called a deformation retraction. I hope it's okay. So I think we can make progress. But the condition here, I have remarked that this condition is sometimes called strong deformation retraction. Strong deformation retraction in the sense that throughout the homotopy, that subset is not changing. Throughout the homotopy, it's not changing with respect to all maps in the homotopy. So let me give you another example of this deformation retraction. You can remember the space. So some more examples of this notion of deformation retraction. For example, this space, if you take X to be the space Rn, the nth dimensional Euclidean space, and A, the subset of the n-dimensional Euclidean space, just a point, that's the origin. The entire space can be collapsed, you can collapse the entire space down to the point. So we have a homotopy that we can start from the identity and take everything down to the point. Okay? Then ft of x is equal to tx is a deformation retraction of the entire space onto A. Yeah. It's a deformation retraction of the entire space onto A. Is it, do we have, how do you define deformation retraction? It should be from identity to the subset, from the identity to the subset. In fact, that's what I'm saying. That no, it should be a homotopy, because I'm talking about this family Ft, defined in this way as being a homotopy from the entire space onto a retraction or down there. So it should be I here. So what is F0? F0 should be the identity on the space. Should be the identity on the space. Okay? And the F1 should map everything, all the entire space, to what? To 0. My subset A. And it should also be the case that F1 of 0, F1 of 0 should be equal to 0. Well, restricted to 0, it should be equal to 0. So we fix this one by writing 1 minus t x, because that is when you will have F0 to be equal to x. Every point will map to itself under the first map. So the first map will be the identity. F0 is f of x equal to x. I hope it's okay. So, and then the last point, if t is 1, you have 0. The entire space will map to 0 when t is 1. And this 0 is also fixed by t. Is it okay? So actually we have a deformation retraction from where? we have a homotopy from the identity to a retraction. So this is a deformation retraction of the space. So the entire Euclidean space can be deformed down to a point. So you can collapse the entire space to a point. I hope it's okay. But you know that Euclidean space is not homeomorphic to a point. You know that? Is it homeomorphic to it? Homeomorphic to a point. The two are not homeomorphic. The real line, is it homeomorphic to just a single point? No, it's not. Why? Dimension not the same. Please. This is n-dimensional, n bigger than or equal to 1. And this one is 0 dimension. So, they are not homeomorphic. So we see spaces may be, even though I have not defined being homotopic, but I will define it. All this I have been saying is we are talking about what? Functions being homotopic. That is, a function f1 is homotopic to a function f0. f0 is homotopic to f1. So, and here f0 is the identity map, and f1 is the is a retraction because it satisfies these properties. So it's a retraction of the entire space onto 0, its subset. So therefore, this space deformation retract to 1 point. So you can collapse the entire space. In fact, any such convex space can be collapsed down to a point in the Euclidean space. Okay? Number 2, we have this, you remember this space X, I cross S1 union over F, Y. You remember this space? The adjunction space obtained by attaching the cylinder to Y along this mapping F. You remember it? So we took A to be our subset and attach. So this is the space. You think of having your space Y here, and then you have the cylinder, and you attach it to Y like this via this mapping. So you can always attach cylinder to a space. So this is Y down there, and this is the adjunction space. So this is our space X. Okay? But you know, because of because of the fact that you have this closed subset down here, you have this closed subset, so you can collapse the entire cylinder down along this line down to this image. I hope it's okay. So the cylinder can be collapsed down to the subset, to the set Y, to the space Y. Okay? So the space, the entire space X deformation retract onto the space Y. You can just collapse it like this. Okay? If you have a cylinder on top of a space, you can collapse it down. In fact, this is general. It doesn't have to be cylinder here, but you know, it's a practical way of demonstrating this thing using cylinder. So a deformation retract via which mapping, which homotopy, onto Y. You can describe the homotopy. so that initially everything is where it is, and then eventually over time, point on the cylinder are just coming down. It is the point on the cylinder that will be moving down, down, down onto the time when they will collapse down to this closed subset. Because a cylinder can always deformation retract to the cycle. Okay? And since you have this mapping, since you know you have the cylinder, so it can always retract onward the cycle. But you have this mapping, you remember it F. This F is a continuous mapping into the space down here. Okay? So, but then you can now map, once you collapse it down, then via this mapping you can now attach it. The entire cylinder can now collapse down to be attached to this, so that you are only seeing the image of the cylinder down there. I hope it's okay. So you can always do that for any such adjunction spaces. Okay? So this is my next example. Next, I will define the concept of homotopy equivalence. Homotopy equivalence. So definition. But then let me remark that so every deformation retract is also a homotopy. Yeah, because it is a homotopy from the identity to a retraction. So already it is a homotopy. I hope it's okay. So once you have a deformation retraction is a homotopy already. So, but that concept of deformation retraction is still a special concept of spaces being homotopic. But let me now formalize it. So a mapping F from a topological space into a topological space. Please, a mapping, continuous mapping. Okay, is said to be so it's called a homotopy equivalence. Or a homotopy equivalence. Let me get equivalence. So this is the concept we are defining. Homotopy equivalence if there exists another map. So if you can find a second map, continuous mapping from Y to X, such that so F, G composed with F, so G after F is homotopic to the identity on X, and F after G is homotopic to the identity on Y. If you can have these maps like this, there is a mapping such that the composite is identity, and this other composite is identity on Y, then the mapping F is said to be a homotopy equivalence. Well, G is also a homotopy equivalence because this definition is symmetric. It's a symmetric kind of, yeah. So if F is homotopy equivalence, then G is also a homotopy equivalent. I hope it's okay. I don't know whether you noticed that when we talked about being homotopic as mappings, if F is homotopic to G, then G is also homotopic to F. Is that so that concept is also symmetric. And if F is homotopic to G and G is homotopic to H, then F will be homotopic to H, so it's transitive. And every mapping is homotopic to itself. So the concept of maps being homotopic is an equivalence relation. It will not be a difficult exercise to check. So this homotopy, so if I say the composite is homotopic to the identity, then identity is also homotopic to the composite. Okay. So if you have such a homotopy equivalence between spaces, then the spaces are called homotopy equivalent. Okay? The spaces X and Y are called homotopy equivalent. Homotopy equivalent. So this is the concept of being homotopy equivalent. Or you say the spaces have or that we say that X and Y have the same homotopy type. Please take note here. We are not saying F and this is equal to identity. So it's not like you are saying F is the inverse of G, but homotopic to the identity. Okay? So don't get confused. Because if you have a continuous map where this is identity, and you know G is also continuous, and this identity is already a homeomorphism. I hope it's okay. So which means every homeomorphism is a homotopy equivalence. I hope it's okay. So this notion is more general than that of homeomorphism. Okay? In the sense that a point is not homeomorphic to, like a disk is not homeomorphic to a point. A disk is not homeomorphic to a point, but the two are homotopic. There is a homotopy equivalence between them. Okay, and maybe we would demonstrate that as an example. Okay, so you say they have homotopy, the same homotopy type, and we write X is homotopic to Y. This. In this case, we say X is homotopic to Y. So please, this is where I'm still emphasizing. You remember I said F naught is homotopic to G naught once there is a homotopy from F naught to G naught. And that homotopy is a family of continuous mapping, continuous family of continuous maps. But throughout that my discussion, I was not talking about spaces being homotopic. I hope it's okay. For spaces to be homotopic, all you need is you don't need a homotopy between them, but you need a homotopy equivalence. I hope it's okay. And a homotopy equivalence is just one single map from one space to the other space. Okay? So that is it. So, so that is it. So once you have that, you have a homotopy equivalence. So let me just give you an example of this homotopy equivalence. Like the disk is homotopy equivalent to a point. But then, yeah. So example, we so you can take the disk. Disk is actually this one called D2 or D2. D2 is okay. And then you can take a point. So this you can be your X, and let this be our Y, the point. So how do you show that they are homotopy equivalents? We define a mapping from here down there. And also show that there is a map G from Y to X, such that F composed with G is homotopy to the identity, and the other composite is also homotopy to the identity. So how do you do it? How can you do it now? So you can define F from X to Y. This is a space with one single point, just Y0, and this is a space of many points. So if you take any X here, you map it to the only point in Y. I hope it's okay. And if you take a point, so maybe if I call this point X0, the central point down there. So, and you can define, well, this mapping is continuous. It's continuous. It's a constant mapping. So, and if you take a mapping from Y to X, so how, I think you don't have, here you have only one way of doing it, sending everything to one point, because there is only one point in the codomain. But here you have so many ways of doing it. If you take the Y naught, is the only point here, where do you map it? Which X? You can map it to any one of the points inside. So infinitely many ways. But then it will be more wise to just say you are sending it to the central point. So you can map it to X naught. You can choose this one, which is the point of the center. And this mapping is also continuous. Yeah, clearly it's continuous. Okay. So, but what happened to F composite, G composite F? Let me start with the other one, F after G. This F after G will be a map from Y to where? So, first of all is from Y to X, and next is from X to where? To Y. So it is a mapping from Y to X. So actually, if you take Y, F composite with G, first F will map it to where? G will map it to X naught. Wherever X is mapped to Y naught. So this is just the identity mapping from Y to Y. So clearly this mapping is the identity on Y. So therefore homotopic to Y. I hope it homotopic to the identity, because you only need to show that they are homotopic. And how about if you take the other one, the other way around? What if I take the other way around is this composite code G after F. This will be from X to X. But if you take an X here, the composite, arbitrarily taking X will be mapped to Y naught, and this Y naught will be mapped to X naught. So it's like every point of the disk is being mapped to only the central point of the disk, X naught. So that is what this mapping is doing. Okay, so this mapping is actually the map that sends everything to just one point. So f of x is mapped to this one for all x in the disk. But is this one homotopic to the identity? That's the question. Do we have a homotopy from the identity down to this mapping? Yeah. Yeah. We can take F naught to be the identity on X. So starting from X and then continuously deforming X down to the point, to the central point. I hope it's okay. Up to this mapping. A mapping that will send everything to. A constant mapping sending everything to. So an F1 so can be the constant map sending everything to X naught. Hmm? Yeah. X naught. No. Because the previous is also G after I is F after G, F after G. No, no. What? Yes, it's the same. Yeah. Just because it's G after F, this is F after G. Yeah. Okay. So there are many points in X, not only X naught. So take any point in X, the F is mapping it to Y naught, like we define over there. And then Y naught is mapped. But what I'm saying here, you have the identity, F naught is your identity, and then you can define a homotopy. So the halfway, F half, will be the mapping sending this to half of this disk. You can shrink it to the half. Are you following? So that at F1, it's already a constant mapping on X naught. So that everything is shrink down to X naught eventually. That homotopy exists. So actually this mapping, even though it's not the identity on X, but it's homotopic to the identity on X. I hope it's okay because this one, F1, is equal to G composite F. I hope it's okay. So there is a homotopy from the identity down there. Is it okay now? So this is it. So but the cycle, you can check easily also that the cycle is not homotopic to the point. Yes. You cannot shrink down a cycle to a point. If you must do it, you must break the cycle open and then shrink it. But once you break, it's not a continuous function. So there is no such continuous map that will do it. I hope it's okay. So we cannot have that homotopy. So you can see that if two spaces are homotopic, then there is a homotopy that will shrink one space to the other. I hope it's okay. In fact, we have a theorem, a result, a lemma, or proposition, maybe 2.1 I'll call it, that if A is a deformation retract of a space, sorry, if X, that is a topological space, deformation retracts to a subset A of that space, then it must be true that X is homotopic to A. If you can deformation retract, then they are homotopic. Are you following? You can prove it, come. So how do you do? So if we suppose it is a deformation retract to A, it means there is a retraction. No. It means there is a homotopy from the identity to a retraction on A. So it means there is identity. So if X deformation retracts So let X deformation retract to A. And suppose this one, that is the homotopy from X is a homotopy It means there is a homotopy from the identity onto a retraction. So suppose it's a homotopy with, that is what it means to be a deformation retraction on A. With what? F naught being equal to the identity on X. That is, the deformation should be from the identity to a retraction. And the second condition is that the F1 should be what? Should be a retraction, meaning it must map everything to A, and F1 restricted to A is what? Is the identity on A. In fact, we can make it a strong deformation retraction as we define for all T. So if this is the case, then we want to show that X is homotopic to A. These two spaces are homotopic. Then it means what? You do what? Yeah. We do the composite. No, I don't understand. We choose what? Not composites. We choose a function f to be our retraction. So we choose f to be equal to f1, so that f is a mapping from x to a, and it's continuous because f1 is continuous. I hope it's okay. So that we show that this f is a homotopy equivalence. And show that f is a homotopy equivalence. Okay? And we consider the map G and take also to see that this is a homotopy equivalent, we have to construct the mapping G. Okay, so we take G to be equal to the inclusion map. So let it be from A to X, because it should be coming backward. To be the inclusion map. That is f of g of x, g of A is equal to A for all A in A. So sending everything to itself, just like the identity map. Then you can see clearly that if you look at the composite f after g, this will be equal to what will be f after g? It should be a mapping from A to where? To A. So if you take any A and map it like this, you get what? F of g of A. But f of g of A will be f of A, because G is the inclusion map. And that will be, but what is f of A? F of A is f1 of A. And f1 of A is identity on A. f1 is identity on A. So even here you can just say T. So f1 is identity on A, so you just A. So which means fg of A is actually identity on A. Okay, so that is fg of A is the identity on A. So a ready-made homotopic to A, okay? A ready-made function that is already homotopic to the identity. So then we now take the other one. So what happened to G after F? That would be what? So if you take any element X in X, that would be G of F of X. Remember, F of X must be a point of A because the entire X is mapped to A. Is that okay? So that was to be F of X. But what is F? Is F1. So that is F1 of X. Since this is happening for all points in X, it means G of this is F1. G of F is F1, yes?
Why are you going to suppose F that marking is not X2Y?
Where?
Because it's there is.
Where? This one?
Yes.
No, we have only one space. Refer back to the definition of deformation retraction. So the homotopy should be from X to X itself because you want to retract down to a subset of X. I hope it's okay. So this is it. So this is G of F. G composed with F is equal to F1. But F1 is what? Is homotopic to F0, which is the identity. So this is homotopic to F0, which is the identity on X. So therefore, this is homotopic to the identity on A, and this composite is homotopic to the identity on G. It means F, that mapping, is a homotopy equivalence. So therefore, what we have achieved is showing that X is homotopic to A. And this whole relation of being homotopic, spaces being homotopic, is also an equivalence relation. It's very easy to show. I hope that is okay. It's an equivalence relation. Yeah, so that is okay. I think we can stop here. So next time we are going to start talking about path homotopy. And then we eventually introduce the notion of fundamental groups. Thank you very much.